So we're going to move from conversation about the derivative to conversation about the integral. The integral is basically defined as the area of the space under the curve over a given interval a to b. So in this case what I've got is I have a curve of f of x is equal to 6, or a horizontal line, over the interval from 2 to 9. So I've drawn that here. Here's the curve f of x. It's just a horizontal line from 2 to 9, and I'm trying to find the area under that curve bounded by the x-axis. So if I'm going to find that, basically all I'm doing is finding the area of a rectangle. So for a constant, the area under a curve of a constant is just going to be defined by the area of the rectangle. And in this case, I can find the length, which is 7, from here to here, over the height, which is 6. So in this case, 42 is equal to the area under curve. Now, if I have a line, in other words, something with a slope, like 2x or 2/5 x plus 1 from 5 to 10, here again is f of x. It's this slanted line from 5 to 10. And if I'm going to take and find its area, you'll notice this is just the shape of a trapezoid. So for any kind of linear function, the area under that curve is defined by the trapezoid that it makes with the horizontal. So we know the area of a trapezoid is 1/2 the height times the sum of the bases. And in this case, the height is defined as the perpendicular, or 5. And the length of the bases can be described by the value of the curve at 5 and the value of the curve at 10. So we could say f of 5 plus f of 10 in that case. So we have 1/2 times 5. F of 5 is 3. F of 10 is 5. And we basically got 1/2 of 40, or 20 for the area under the curve. Now, where things get difficult is when our functions are not linear anymore. They make some curved function. So for instance, this function here is the shape of a parabola, and I want to find the area of the region under that curve bounded by the x-axis from 2 to 8. Much, much harder, because once again I can't make a rectangle, I can't make a square, I can't make any kind of trapezoid. It's just a difficult prospect. So what we're going to do is kind of do probably what you did back in elementary school. We're going to approximate this area under the curve by cutting it up into little chunks. And the easiest chunks we could probably make are like rectangles. So if I were to say, well, let's take some rectangles and put them inside here, like so, and found all those areas of those rectangles, I could take and approximate the area of the curve. But the problem is, you notice that all these little pieces right here are not included. So I'd have to know that this is just an approximation. Well, if I take a look and do those rectangles nice and evenly, here's again an idea of kind of what this looks like. But again, you'll see here these open spaces that are not included in my calculation. Also, you'll see I have some rectangles that are over space. So you'd think that maybe some of these overestimations and underestimations will cancel each other out, and I'll get pretty close to a good approximation. One thing you can see though is that if I take and make more rectangles, I have smaller spaces of under approximation and smaller spaces of over approximation. And again, they may fill in each other just a little bit, maybe not the same, but I'll get a better approximation the more rectangles I make. Again, if I make even more rectangles, you can see that the over approximation spaces and the under approximation spaces are even smaller, and thus when I fill them in, my approximation for the total area under the curve will be even better. Now there's a couple of different ways we can draw rectangles. We can draw rectangles using left endpoints of a given Now there's a couple of ways we can choose to make these rectangles. We can make our rectangles with I don't want to say that. Now there's a couple of ways we can make our rectangles. We can make our rectangles referencing a leftmost point on our interval from A to B. So you'll notice that in this case, all my rectangles start with a left point on the curve. Whereas in this case, all my rectangles are going to start with a right point on the curve. And in this final case, you'll notice that our rectangles are made such that the middle of the rectangle goes through a point on the curve. So these are all ways to make approximate rectangles, and you can see that if I'm using this leftmost, I'm under approximating my answer. The rightmost, I'm over approximating my answer. And when I do a midpoint, we get both an over and under approximation, which seems that the midpoint would probably be the best way to get a decent approximation for our curve. So what we're going to do now is we're going to take and find the area under the curve from 0 to 12 of this parabolic function here using 4 subintervals and the right endpoint. So to calculate these intervals, I take my interval of 12 to 0, subtract that, and since I want 4 intervals, I'm going to divide by 4, giving me a delta x value of 3. So every 3 units I'm going to go along this axis and say, well, here's where I'm going to draw rectangles at 3 units apart, and then I'm going to identify the rightmost part of the curve at that interval in each point and use that as corners of rectangles and then calculate those rectangular value areas. So drawing my rectangles from the rightmost point on the curve down, and now I'm going to calculate those areas by taking 3 times, in this case, f of 3 times, in this case that's f of 6, 3 times f of 9, and 3 times f of 12. Those values are as follows: 36, 32.6, I'm just going to round to the 10th, 22.5, and about 5.6. And that's going to get me a total of about 96.7. Again, this is an under approximated value because in this case I'm a little over, quite a bit under, I'm a whole lot under here, and even more under here. Now let's go and approximate these values using left endpoints. Again, our delta x is going to be 3, and I'm going to mark every 3 spaces once again, so 0, 3, 6, 9, 12. And in this case, I'm going to identify where I am on the curve at the leftmost part of that interval and draw a rectangle from that left point over to the end of the interval in each case. So you can see the circles that I'm drawing are the leftmost parts of those intervals of 3. So in this case, I'm going to find 3 times f of 0 in this case, 3 times f of 3, 3 times f of 6, and 3 times f of 9 in this case. F of 0 is 32.6. F of 3 once again is 36. F of 6 is 32.6. And F of 9 once again is about 22.5. I'm going to add these numbers up, and I get about 123.7. Now you'll see that that is more than 96.7, and it should be, because I have a small under-approximated area here, about a little less over-approximated here, much more over-approximated here, and greatly over-approximated here. Now we're going to take and find the area using the midpoint approximation with the 4 subintervals of delta x equaling 3. So here once again are my intervals of 3 being marked, but instead of going to the left or right of the interval, I go right to the middle. So in this case, I'm at 1.5, I'm at 4.5, 7.5, and 10.5, which means I need to calculate my areas of 3 times f of 1.5, 3 times f of 4.5, 3 times f of 7.5, 3 times f of 10.5. Then I'll add those all together again. And this time I have values of 35.2, 35.2 again, which you can see in the picture, 28.4, and 14.9. Giving me a final value of about 113.7, which again should be somewhere between the other two. Here's 123, 96, and 113 is a much better approximation because little over, little under, little under, little over, a little bit more under, a little bit more over, a lot more under, but a lot more over. So hopefully this is pretty close to the exact. And we will find the exact by using our calculator in just a minute after I explain a couple of things. So what we've done now is we said the area under the curve of any function is equal to the sum of the area of rectangle partitions of the function. And as the number of partitions increase, the area approximation gets more accurate. Notation for the sum of the areas or the integrals is this following equation. This states the integral from a to b, that's your interval, of f of x. So basically it says sum of all rectangles from a to b. And remember, we have tons of rectangles. So like our delta x is going to be 0.00001. All right, which means I have infinitesimally small rectangles in width to calculate the area of, and I'm getting a real close approximation of the answer. Now to do this on our calculator, for this same function, we're going to do the following. Turn that guy on, we're going to go to y equals first, plug in our function. Function is going to look very similar to what we're doing here. I have x min at 0, x max at 12, looking at a y min of -1 and a y max of 14. Once again, make sure your fractions in parentheses and your x minus 3 term is in parentheses when you square it. Then we'll go back to our main screen, hit the math button. If we go down to number 9, I believe, you'll see this fn int. That's going to find the integral of our function, so we want to type that in accurately, negative parentheses 1 divided by 8 times the quantity of x minus 3 squared plus 12. And then what we're going to do is comma x, that's the variable we're using, beginning number in our interval, comma 0, ending number in our interval 12, close the parentheses, hit enter. We get about 112.5. We just approximated using that midpoint of 113.7. It's a pretty close approximation using only 4 rectangles and a delta of 3. If I made my delta 0.0001 like we were talking about, we're picking up basically, like I said, about 7/10. So our area is equal to 112.5. Alright, and that's how you use that calculator to find the area. Write your lesson summary, do your My Math Lab, and we'll chat more about this tomorrow.